today's discussion, we'll discuss what are magnets, what are the properties of magnets, and then what are the magnetic lines of forces, their properties, and we'll see how we can draw the magnetic lines of forces for some special cases there or some specific cases. We'll also discuss, if you see the properties of the magnets, we say that like poles of the magnet repel and unlike poles attract. Now, can there be force of attraction between like poles of the magnet? And at the same time, can there be force of attraction between like poles of identical magnets? So we'll discuss all this in today's discussion. So first of all, when we define magnets, magnets will be those substances which can attract other magnetic substances there, and they possess directive property. So they will be attracting other magnetic substance like iron, cobalt and nickel. And if suppose they are suspended freely, they will get aligned in the north-south direction if you take a magnet there. So now let's discuss properties of magnets. We can classify magnets in two categories. One will be the natural occurring magnets and other will be the artificial magnets. Natural occurring magnets are usually weak magnets and they are also of irregular shape. But artificial magnets are the strong magnets there. They are designed and they are produced as per the requirement there. So they will be of a specific shape. They will be relatively more stronger there as compared to the natural magnets. Let's take properties of magnet. First property is like poles repel and unlike poles attract. If you take like poles of the magnet, north-north pole, they will repel each other, north-south they will attract. So like poles repel and unlike poles attract. Like poles of the magnet, like if you have the north pole and north pole, they of the two magnets there, they will repel each other. If you have the north pole and south pole of the two magnets, they are brought close, they will attract each other. Another property is that magnet possesses directive property. Directive property means if you take a magnet and you suspend it freely, it will get aligned in the north-south direction. So that is the directive property. You take a bar magnet, you suspend it freely there, it will get aligned in the north-south direction there. So this is your directive property of the magnet. Another is magnets possess inductive property. That means if you bring a magnet close to the magnetic substance, it will induce magnetism in the other substance. Like if you are bringing magnet close to another magnetic substance, like suppose you have another iron piece there, in that case it will induce magnetism in the other. So it will develop the magnetic poles there, and then there will be magnetism acquired by the other magnetic substance also. So it can induce magnetism in the other magnetic substance or a magnetic material there. Monopoles do not exist, or magnetic poles always occur in pairs. That means if you have a magnet, then it will have the north and south pole both occurring together. You cannot have isolated north pole or isolated south pole there. Suppose you have a magnet, and if suppose we take this magnet, this is the south pole, this is the north pole. If I cut it into two parts, then we'll not have the south pole and north pole separate. It will develop the magnetic poles again. So here on this side, there will be north pole developed, here there will be south pole developed. So in this case, you will not have the isolated south pole or isolated north pole. Again, you will have the magnetic poles occurring in pairs. So these are some of the properties of the magnets. So these are just a statement there. Now let's just do them in detail. So for the first one, we say like poles repel and unlike poles attract. Now it is asked, suppose it is asked, can there be force of attraction between like poles of two magnets? Between like poles there is repulsion. But is it possible that we can have the force of attraction between like poles of the magnet ever? This is possible if the strength of one magnet is very large as compared to the other one. Suppose you have a magnet here. This is the south, this is the north, this is the another one, north, and this is south. Now this one is a strong magnet. Suppose this is a strong magnet. So if this is a strong magnet, so it will induce magnetism. So it will induce other magnetic pole close to this end. So here this one will develop a south pole here. Remember, this magnetic pole, that is the north pole of the other magnet, that will also induce magnetism in this. As the strength of this pole is less, so it will induce less amount of magnetism in this one. Here the strength is more, so it will induce more magnetism in the other case. So there will be south pole developed here, north pole here. Now between this north pole of this strong magnet and north pole of this weak magnet, there is a force of repulsion. But as the strength is more and it has induced magnetism in the other one, so there is the south pole developed for this end. So there will be force of attraction between these two. North pole of this magnet and other induced pole on the other magnet there. So there will be force of attraction. And as the strength is large, so definitely this force of attraction will supersede or it will exceed the force of repulsion between the two. As a result, net force will be attractive. So there will be a force of attraction between like poles of the magnet. But that is only possible when the strength of one magnet is very large as compared to the other one. Now, if it is asked, is it ever possible that between the like poles of two identical magnets, there is force of attraction? Definitely you will say, if it is identical magnets, it is not possible. But in fact, one of the students has shown me, or to his whole class there, identical magnets having the force of attraction between its like poles. And do remember that when they have shown the magnet, the poles were not wrongly printed there. Because if the poles are wrongly printed in one of the magnet, so what is printed is that north is basically a south one. So there can be a force of attraction there. But poles were not wrongly printed. They were the identical magnets. Still there was force of attraction. And it has been shown there. But there was one thing which they all have missed. In fact, this particular incidence is a real one, and that particular student has his elder brother 3 years senior to him, and his father used to teach them. So when the elder one was in class 8, so just to explain the properties of the magnet, his father has purchased one magnet, and he explained the properties of the magnet to his elder brother. And after that, that magnet was kept in the shelf. When this boy has come in class 8, 3 years later, his father was aware that the magnet which was kept in the shelf has lost its magnetic property. So he purchased another magnet to explain the properties of the magnet to the youngest one. And now this boy has got access of two magnets, the old one and the new one. since the old one was kept in the cell without mishandling, so appearance wise it was as good as a new magnet, whereas the new one was basically a strong magnet. So the old one was a weak magnet and the new one was a strong magnet, although appearance wise they were all similar. So they were confused that these are the identical magnets. They were identical only in appearance, but not in terms of the strength. So here also when we say that can there be force of attraction between like poles? This is possible only when the strengths are different. If one magnet is very strong as compared to other, then there can be force of attraction. But if the identical magnets are there, in that case it is not possible. Identical means identical in all respect. That is especially in the strength. And they were confused with the identical means identical in appearance. So they looked identical, but strength-wise they were different magnets. Another is that a magnet possesses directive property. If you take a magnet and you suspend it freely, it will get aligned in the north-south direction. So suppose if it is asked that if you have been given two identical iron pieces, one is a magnet and other is a simple iron piece, how will you distinguish between the two? So one method can be there, that will suspend them freely, and if you suspend them freely, the magnet will get aligned in the north-south direction and the iron piece will get aligned in any direction. So if you are aware at that particular place which is the north-south direction, so you can easily say which is magnet, which is iron piece. But for any other place where you are not sure which is the north-south direction, so once they get settled, we slightly disturb them. Like if this gets settled there, we'll slightly disturb them. So the magnet will just oscillate about its mean position, whereas the iron piece will get settled in any orientation. It may turn there, it may complete one circle, or it will finally settle at any orientation. So there, that will be the difference between the two. Magnet will be just oscillating about its mean position if it is slightly disturbed from its equilibrium, whereas the iron piece will get aligned in any direction. Of course, for the other cases also, even if you consider or if you know that which is the north-south direction and the iron piece and magnets have settled down, there also you should slightly disturb, because it is possible that the iron piece which gets settled in any direction, incidentally it may get settled in the north-south direction also. So the best will be that you slightly disturb from that position and see where it gets finally aligned. So that gives the distinction between the two. But in this case, we need a thread to suspend these magnets. If the thread is also not given and you have to distinguish between the two, which is iron piece and which is magnet, so how will we distinguish that? For that, what we do, we take the magnet or the iron piece and we put them, one of them, on a flat surface. We either may put it horizontally in our hand or we can put it on the table surface there. So suppose one we have placed like this, and the other one, what we'll do, we'll move it from one end to other. This will be moving from one end to other. So if suppose this is one piece lying on the table surface, we'll move other one from along its length from one end to other. Now you know that for magnet, its magnetic property is maximum at the ends and minimum in the middle. So if we assume that this is suppose the magnet which is kept on the horizontal surface and the other one which we are moving, so now it is the iron piece which is, if it is at one end, it is the north pole or south pole, and the one end of the iron piece. So there is force of attraction, and this force will be maximum. As we move this along its length, so the force of attraction will get decreased, or it will decrease till we reach the midpoint. And after that, it will again start increasing because we are approaching the other pole. So if there is a variation in the force, one which we are moving is an iron piece and the other which is lying on the surface is a magnet. Whereas if you take the just reverse case, if this is suppose the magnet, this is the south and north, and this is the iron piece, and if we are moving it from one end to other, it is the one pole of the magnet which is being moved from one end to other. And if it is being moved in that direction, so there will be uniform attraction all along its length. So if there is uniform attraction experienced by one which we are moving along the length of the other one, then one which we are moving is a magnet and the other which is lying there is a simple iron piece. So this is how we can distinguish between the two, where you have not been given any thread there or any magnetic substance or anything else there to distinguish between the two. So these were some of the important properties of the magnet. There were some conceptual type questions which will help us to understand the properties of the magnets in detail. Let's now discuss magnetic lines of forces or magnetic field lines. Magnetic lines of forces are the imaginary lines. Tangent to them at any point gives the direction of magnetic field intensity at that point. So it is just similar to electric lines of force. Electric lines of forces also we define as the imaginary lines tangent to them at any point gives the direction of electric field intensity at the same point. So here also for the magnetic lines of forces we get in the same way. So these will be the imaginary lines tangent to them at any point gives the direction of magnetic field at that point. Or it can be defined also as the path followed by a unit north pole if it is free to move. So you have a unit north pole, you allow it to move freely. So whatever path that unit north pole will possess or will follow, that will be the magnetic lines of force there. So now let's take properties of magnetic lines of forces. So the property is magnetic lines of forces originate from north pole and terminate on south pole. But they originate from north pole and terminate on south pole. That will be there when we take it outside magnet. Inside magnet they move from south pole to north pole. So because that is the another thing or another property you can say that magnetic lines of forces form closed loop. Electric lines of forces do not form closed loops, but magnetic lines of forces they possess or they form closed loop, because if you have magnet here, suppose this is your south pole, this is the north pole, so the magnetic lines of forces will originate from north pole and they will terminate on south pole. So they are basically, you can say they are moving like this there, but at the same time we have the other lines of forces also there, but inside they move from south pole to north pole in the magnet. So here they are forming closed loop. Here also we can say that as they originate from north pole and terminate on south pole outside the magnet, inside they move from south pole to north pole. So this is how they form the closed loop. Now why it is so? Because the monopoles do not exist. So they will be forming closed loop. Wherever you have the north pole, there will be a south pole. So they will always occur in pair. Whereas you can get isolated charge there, You can get isolated positive charge, you can get isolated negative charge. So there they do not form closed loop. They just originate from positive charge and terminate on negative. Another property is that they start and end on the surface of magnets normally. Just like the electric lines of forces, they meet a surface normally there, or conducting surface normally. Here also, whenever they will be meeting a magnet there, they will meet there normally there. Another property is magnetic lines of forces do not intersect. Because if they intersect, in that case at the point of intersection there can be two tangents drawn indicating the direction of magnetic field at that point. So at same point there can't be two directions of magnetic field. Definitely they cannot intersect. It is just like you have suppose one magnetic lines of force like this, other is this one. If they are intersecting at this point, I can draw tangent to this point corresponding to two curves there, and these two tangents then they will indicate the direction of magnetic field. Here B1 and this is your B2. So at the same time you can't have two different directions of magnetic field. So this is not possible. Next property, number of lines of forces per unit area normally is proportional to the strength of magnetic field. Or you can simply say that relative closeness indicates the strength of the magnetic field. So just like you have the number of electric lines of forces acting per unit area proportional to the giving you electric field intensity at that point. In the same way, number of magnetic lines of forces per unit area about the point will give you the strength of the magnetic field at that point. Obviously, if you have more number of lines of forces per unit area, the strength will be more. If it is less number of lines of forces, field value, magnetic field value will be less. And that is also, it is indicating that relative closeness. If you have more number of lines of forces per unit area, that means lines of forces will be more compact there. They will be more close there. So strength will be large. And if it is less, in that case, that will be lesser value of magnetic field intensity. So this relative closeness can easily give you idea how the magnetic field are there in the two different points where the numbers are different. So these are some of the important properties of magnetic lines of forces. Now we'll see how we can draw the magnetic lines of forces to some cases, then it will be more clear. If you consider that the current is out of the plane, it is a current wire carrying current and it is coming out of the plane there. So magnetic field due to this one will be in the anti-clockwise direction if you apply thumb rule there. So in that case, this will indicate the direction of the magnetic lines of forces there. So if you consider here magnetic lines of force, it is forming a closed loop there. And if you take now its direction at the different points, so in this case, at this point, it is in this direction. Here it is in this direction. Here it will be downward. This will be towards right. So you can get the magnetic lines of forces direction at that point. If you draw it in totality, you will get a circular ring there. So you will get a circular ring representing or circle representing the magnetic lines of force there. And at the different points, you can get the magnetic lines of forces having different value there. But suppose you have a wire which is carrying current. Now this time you have the wire which is carrying current. So if this is the wire which is carrying current in the anti-clockwise direction, so what will be the direction of the magnetic field? Magnetic field will be in this direction. Because if you apply right hand thumb rule there, the curled fingers are in the direction of current. Thumb is indicating direction of magnetic field. So it is in this direction. So magnetic lines of forces, if I have to represent, it will be moving like this. And they will be coming back from this side. That means they will move like this and they will come up. And you can see here that as they are coming out, you can treat as if there is a North Pole there and below that there is the South Pole. So the lines of forces are coming out of the North Pole and they are terminating on the South Pole that is just below it. And again it will be forming a closed loop there. So they will be like moving here and coming back. Okay. This will also come and go like this. And some will be going and following a larger path to come back. So this will indicate how the magnetic lines of forces can be there if you have the wire which is carrying current. Same will be there if you are representing magnets there. If you have the magnet, like if this is suppose South Pole, this is the North Pole, in that case lines of forces will be coming out of the North Pole and on the South Pole they will be terminating there, and inside that it will be moving like this. These will be like some will be going and coming back. So this will be the representation of the magnetic lines of forces. If you take Gauss theorem in electrostatics, we have E dot ds over closed loop as Qi by epsilon naught, where Qi is the net charge enclosed there. And if you take the Gauss theorem in magnetostatics, this is your B dot ds equals to mu naught into M, where M will be the pole strength, or that is also called as the magnetic charge there. Earlier it was called as the magnetic charge, now we are using the word pole strength there. Now since monopoles do not exist, so whenever the poles will appear, they will always appear in pair. And if they appear in pair, the net pole strength will be 0. So B dot ds will be 0. Now just see how we can apply this to explain the properties of the electric and magnetic lines of forces there. Suppose you have an electric dipole. You have electric dipole, this is your minus Q, this is plus Q. If you consider the electric lines of forces, then they will be originating from the positive charge and they will terminate on the negative charge. If I take any closed surface here and I want to apply Gauss theorem, then E dot ds, this will be equals to Q by epsilon naught at this place. If I take the same here, in that case it is your E dot ds integral over closed loop. This is minus Q by epsilon naught for this surface, and this is for the other surface where you have positive charge there. Because inside this imaginary surface we have only the charge Q there. But if I take a magnet, here if you have this as the South Pole, this as the North Pole, so lines of forces will originate from here, they will terminate here. In terms of the pole strength, if I take, suppose this is plus M and this is minus M. So now again if I take a surface here, closed surface, in that case B dot ds, if you apply here, it has the pole, that is the North Pole there. So lines of forces are coming out, in that case it will give you how much? Mu naught M. But in magnetostatics we get that this term should be 0. Similarly here if I apply, in this case how much it should be? B dot ds integral, this should be mu naught into minus M, which is wrong, because according to Gauss theorem of magnetostatics it should be 0. How you can get 0 there? Here you see you have the lines of forces originating from North Pole, but they are coming out of the North Pole and terminating on South Pole outside magnet. Inside magnet also we have the lines of forces there, moving from south to north. So if I take here, suppose the lines of forces are originating from north, they are also reaching also there. So this will be not only just M, it is minus M or it is 0, because net lines of force there, if you consider, it will be 0, because you have the lines of forces coming out and reaching also there. Here also lines of forces, they are reaching, at the same time they are leaving also. So again in this case, if you consider, it should be equal to 0. And this is possible only because magnetic lines of forces, they form a closed loop. And they form closed loop just because you cannot get isolated North Pole or South Pole. In dipole, it is possible because you can have isolated North Pole, you can have isolated positive charge, isolated negative charge. We can get isolated charges there, but we cannot have the isolated poles there. So this we can easily explain that why it should be 0 and why the magnetic lines of forces form closed loop. So this is all about the properties of the magnetic lines of forces.